Hi everyone, this is Manas, your friend and tutor. And guys, welcome to the brand new lecture series on mechanics of solids. The topic of discussion for today is going to be the same that we had in the previous session. That is simple stress and strain. Now, if you haven't seen the previous session, the link to that can be found in the description down below. Go ahead and watch that video where I had discussed all these topics in depth. Okay, now that video got a bit too long, more than 1 hour. So I thought, why not discuss the remaining part of the stress, strain and curve for ductile material in this video, that is part 2. So we are going to kick off with today's session and we are rather continuing part 1 in part 2. So what we've basically done is we have done an experiment, and what are the results of that experiment? Based on that we've made a plot. So if you are asked in an examination to make the plot of a stress strain curve for say a ductile material, in this case it's a mild steel which is a low carbon steel. So low carbon steel corresponds to a ductile material, okay, also known as a mild steel. When you do this experiment, right, when you put that mild steel specimen under investigation in a universal testing machine and you punch 2 dots, the distance between them is known as the gauge length, that has to be taken as 50 millimeters. The results that you are going to get is as follows. Number 1, if you keep on increasing the load, well, obviously the value of stress is going to increase and the strain will also increase, okay, very less compared to the remaining strains that we have, but there is going to be some deformation. So before the elastic limit, or rather I should say at the proportional limit, the strain that we will obtain is 0.0012. okay, that is the change in length with respect to the original length. The original length is 50 millimeters. There must have been some change in length, and when that division takes place, you are going to obtain this value. Now, beyond this proportional limit, the material is no longer elastic. Now guys, there is always an issue of obtaining proportional limit and elastic limit. Let me tell you, when you do this experiment, this proportional limit as well as this elastic limit, EL, they are very close to each other. So what I have basically done is that I have considered only one single point. Let's say that the proportional limit and elastic limit have coincided, right? Now, if you go beyond proportional limit, the material is no longer elastic. That means even on the removal of load, the material will not regain its original shape and size. So, before PL, there is elastic behavior, and after PL, that there is plastic behavior. That means even on removal of load, the material will not regain its original shape and size. That's plastic behavior for you. Okay. Now, this proportional limit is reached corresponding to this 241 megapascals. Remember, this is in megapascal and the strain is actually unitless. You can also say strain is basically a ratio of change in length to original length. You can also write it as mm per millimeter. In some of the books you will see this notation, right? So basically it is a fraction. What happens when you go further? If you go further, there comes a point where yielding happens. And what is yielding? Let me tell you. At 262 megapascal, what will happen? You don't have to increase the load, okay? So don't actually open the valve of the universal testing machine. Let it be. What will happen, or what rather you will observe, is there is going to be a slight dip, very slight dip, and then you will observe that even when you don't apply load, still deformation is taking place, or rather considerable or appreciable amount of deformation is taking place, and the stress values between those 2 points is 262 and 248, and this is the upper yield point and this one over here is the lower yield point, and the difference is very less. That's why we say that yielding at constant stress is taking place, right? Okay, so that was yielding for you, right? An appreciable amount of strain without any increase in applied load or without any increase in stress. Then, okay, that yielding actually gets over at 0.03. And then finally, this is the region where the material regain its strength. This region from Ly to U is known as strain hardening, where the material regains its strength. Now that value has to be worked out as 435 megapascal. Now you might get a different value, but it should be close to this value. Okay, it should be very close to this value. These are all the experimental results which you are going to get if you perform this tension test on a mild specimen on a universal testing machine. So that's it. And finally, after this point, neck begins to form, and at point F, the material finally fractures. So the stress at fracture is 324 megapascals. And at fracture, the strain is 0.38 times. So these were all the data which you are going to get when you perform the tensile test on a universal testing machine on a mild steel specimen which is having two dots separated by a distance of 50 millimeters. That is the gauge length. Okay. Now, there is something which I need to tell you. There is a parameter in the form of ductility. And what is exactly that ductility? It is the ability of a material to undergo large strains before rupture is a quality which is known as ductility. So in this case, you can actually get the value of ductility, and it can be judged by two different parameters. One is the percentage elongation, while the other one is percentage reduction in area. So if the material is able to undergo large deformations or large strains before rupture, then the material can be regarded as ductile in nature. And if it is not able to do so, then that material is brittle. Okay. So if a material exhibits very little or absolutely no yielding before rupture, then that material is brittle in nature. We'll also talk about that. Okay. Grey cast iron is one such example which is brittle in nature. And we'll see what happens to that specimen when it undergoes tension and when it is undergoing compression. We'll see all of that coming up. So here we have percentage elongation. This is the change in length divided by the original length. We already know what the change in length is. This is delta L divided by the original length, and that is nothing but the strain, and this is working out as how much? 0.38. This ratio in fact is working out as 0.38. This is what I am talking about, 0.38. okay. When you multiply that by 100, you will get this value as 38%. So you can just take a look at this. Initially it was 50 millimeters around, okay, and now the total length will be 50 plus 0.38 times of 50. You can actually get this value. So that is the final length of the mild steel specimen before or just at the moment of fracture. So this is how you can work it out. So basically percentage elongation and percentage reduction in area are the two parameters or factors which will help you enable or help you judge whether the material is really ductile or not. Okay. Now let's take this session forward and let's now talk about a brittle material which is a grey cast iron. Now brittle materials are those which undergo little or absolute no yielding before rupture. Now when you talk about grey cast iron, if you just do a tension test and a compression test on a specimen of grey cast iron, the results are very sort of weird. Let me just tell you, if along this y-axis let's say we have stress, and along the x-axis let's say we have strain, okay, and this is negative strain, why? You'll realize this very soon, and this is negative stress. So this region is for tensile test and this region is for compressive stress. In compressive stress, the elongation, there is not going to be any elongation, okay. In compressive stress, the material's dimensions will reduced, and compressive is opposite to tensile. That's why you'll see a negative sign over here, okay. Now if you try to make a plot, there is going to be a region over here and here, and in compression test, now you can clearly see that the material fails at this point. That means there is fracture, and this region is for tension test and this region is for compression test. Now if you try to observe this figure here, this is the strain undergone before rupture in case of compression, and here the material actually breaks, okay, there is a rupture, and here this is the strain when this specimen had undergone the process of tension. Now if you watch carefully, the strain along compression is greater than the strain in tension. So this question might be asked to you directly in the examination. Which one of the following options has or exhibits more strain in compression than tension? And grey cast iron is one such example where it is going to exhibit more strain when the compression test is going on compared to tension test. That's it. Now let me just get into the details of stress strain curve. Okay. Previously we saw the stress strain curve of a mild steel bar. There are some more materials which also have the similar characteristics. We have already seen the stress strain curve of a mild steel bar. Now if you just go by phase, initially it is going to show elastic behavior. Okay. Now this elastic behavior is then succeeded by what? Yielding, isn't it? Then there is going to be yielding. Yielding is then followed by strain hardening. And once strain hardening is over, this is then followed by necking. And necking ends with rupture. Necking until rupture. That's it. Now, these are the four phases. And there are some more materials which sort of show these characteristics. Those materials are zinc. If you try to do a tensile test on a zinc, that is also pretty much going to show you this elastic behavior initially. Then there is going to be yielding, that is at constant stress, followed by strain hardening, and then there is going to be necking until the material ruptures or fractures. Zinc, then there is molybdenum, and also brass. These are the materials which also show the same property or stress strain characteristic just like a mild steel bar does. But there are some materials which do not follow this. One such material which comes to my mind is an aluminum alloy. Now this material is such that although there is going to be a proportional limit, but there is no specific yield point, and things get very difficult. No specific yield point. Okay, so in order to get the yield point, there is a method which we use. It's a graphical method. Let me tell you, it's a graphical method, and that method is actually known as an offset method. Now let me just show you how that works out. Let's say we are doing the testing on an aluminum alloy. Here we have strain, here we have stress. Right? When we do the testing, this is the kind of plot that we get, and then there it is. You will not be able to detect where the yielding happens, right? In such a case, we actually follow an offset method to predict the yield point. And in this offset method, we actually do this 0.2% strain. So here we already have the strain, and 0.2% strain would be somewhere here. That means the value would be 0.2%. That means 2 divided by 100 will be what? 0.002. This is going to be 0.002. So from here this is 0, and at a distance of 0.002 on a scale, you need to just mark a point. Okay, this is offset. And with respect to this initial line, you need to draw a line parallel like this. Wherever it intersects this stress strain curve, that point is going to give you the yield point. So this methodology comes in very handy, especially for materials which do not have a precise or a specific yield point. So try to use this offset method. Now a question might be framed in the examination. Which one of the following methods, or which one of the following materials, in which one of the following materials will you apply the offset method for knowing or for detecting the yield point? Options are zinc, molybdenum, brass and aluminum. So you now know what the right option is. There is clearly a yield point in these three metals, but as far as an aluminum alloy is concerned, the yield point is very hard to detect, and there you are going to use the offset method to determine that. So that was all about stress strain curves, and now let us take this session forward, and we are going to see and learn about these fellows. These fellows are the elastic constants. Okay, and why are they called elastic constants? There is a reason for that. So let me just remove all of this. Now, elastic. What do you mean by elastic? First of all, any material can be regarded as elastic if it is able to regain its original shape and size on removal of load. Okay, now you can apply load in a bunch of ways. What you can do is, let's say we've got a bar like this. It's basically a rectangular bar, and we apply a load over here. What is going to happen? There is going to be some elongation like this, isn't it? There is going to be some change in length, let's say delta L. If you want to find this change in length, this modulus, which is known as Young's modulus, will be helpful. And how both of them are related, I'll tell you one by one. Okay, so these elastic constants are such that they'll try to help you find the deformations. What sort of deformations? Let me tell you, they are linear deformations, linear and shear strain. What exactly is that? We'll come to know in modulus of rigidity, but for now you can just say that the elastic constants help you to judge and mathematically calculate the change in deformation. Now that deformation may be axial, that deformation may be lateral. All the things can be worked out pretty easily with the help of these elastic constants. But remember, the experiment that you do or the analysis that we'll do will be as long as the material stays elastic, Okay, now first thing, we'll talk about Hooke's law. You just watch this figure. It's a stress strain curve that we have drawn. This is strain and this over here is stress. If you just draw the stress strain curve, you'll have a plot like this. This is proportional limit, yielding happens like this, isn't it? And then there is, over here we have ultimate stress, and this is where it fractures. This is the proportional limit. And if you watch carefully, this is sigma PL. And if I can just work out sigma PL, not sigma PL, this is, what is this? This is strain. This strain actually worked out as 0.0012 if I am not wrong. Let me just check in my notes. This actually worked out as 0.0012. Yes. And then secondly, the stress over here, sigma PL, actually worked out as 240 megapascals, isn't it? Now you watch here, if you consider 2 points, then this is going to be the slope. If you again consider 2 points, this is going to be the slope. You can clearly see that the slope along this line is going to remain same. Okay, so the slope of stress strain curve is represented by a modulus, and this modulus is nothing but the Young's modulus, known as Young's modulus. And Young's modulus is represented by E. E is equal to what? Slope of what? Stress strain curve. And you know very well, if you want to know the slope, this is change in y divided by change in x. That is the slope, okay, and which is going to be equal to stress divided by strain. Now strain is actually unitless, you can say. This is in pascals, so the unit is going to be what? Pascals. Well, you can also go ahead and get the value of the Young's modulus for a mild steel specimen. Guys, we already know this, and we know this also. Okay, so you can actually calculate the value of Young's modulus for a mild steel. Let me show you what that will work out as mild steel. Now we know what is it? Stress, proportional limit, strain, proportional limit. You just have to do this division, and this is how much? This is 240 megapascals. Mega means 10 raised to 6. This is pascals, and divided by strain is what? 0.0012. You just do this division. So when you do this division, there is going to 240 into 10 raised to, this is 12 times of 2 is 24. This is precisely going to work out as 200 into 10 raised to 9 pascals, or you can also write it as 200 gigapascals. Therefore, the Young's modulus in case of steel will work out as 200 gigapascal, and this is something which you will encounter amongst all the problems where steel is the material. Okay, so the Young's modulus for steel is going to be equal to 200 gigapascal. And there is one more coincidence. Value of E for a soft steel, for a medium carbon steel, for a hard carbon steel, for a machine steel, or for a structural steel, for all the different types of steels, the Young's modulus value will remain same, that is 200. And why? There is a specific reason for that. We'll come to that point, but I'm pretty much sure now you must have understood the entire idea of Young's modulus. So how can you define Young's modulus? Young's modulus is defined as the ratio of stress to strain before the proportional limit, or as long as the material remains elastic. That's it. And what about Hooke's law? Hooke's law. So this is exactly Hooke's law. The definition of Young's modulus is the actually what do you call? Is actually the Hooke's law. It is the ratio of stress to strain. Simply, it is the ratio of stress to strain. Ratio of stress, I'm writing it in short, to strain. Okay. You can also say that the slope from Hooke's law, you can also, what you can conclude is, from Hooke's law, the slope of stress to strain is represented by a factor, represented by a moduli, or represented by an elastic constant. Elastic constant, which is represented by E, which is equal to stress upon strain, and the value of E that is worked out for a mild steel is equal to 200 gigapascal for sure. Okay, now let me tell you the reason why the value of E for different types of steels works out as 200 gigapascal. You'll understand this. So guys, in order to understand why the Young's modulus for steel for different variety of steels always works out as 200 gigapascal. So what we have basically done is that we have conducted the tension test on a universal testing machine for different variety of steels. Okay, and we have made a plot of all of them on a same graph paper. Let's say what we see is that before the proportional limit of all these, so before the proportional limit of soft steel, before the proportional limit of structural steel, that of machine steel, hard steel and spring steel, if we just try to make a triangle over here and try to take the slope M for soft steel. Okay, and again if you make a triangle over here and you try to work out this slope, which is equal to M of what steel? This is structural steel, and the slopes of different kinds of steel, all of them work out as the same value. That is why the Young's modulus of steel is always going to work out as, for different variety of steel, will always going to work out as 200 gigapascal. This is the main reason why. So this question might be asked to you, some of the mechanical engineers in universities. Why do different variety of steel have the same Young's modulus? The reason is very clear, that the slope before the proportional limit, there is a linear relationship between stress and strain, and the slope before the proportional limit for all of them is same. Okay, and then the pattern might change. Their ultimate strength value will gradually keep on increasing, going from soft to spring steel or a hard steel. But the one thing that remains constant is the characteristic before the proportional limit for all of them, which is represented by Young's modulus, which is nothing but the slope, right? So this was the main reason why the value of steel or Young's modulus for steel will work out as 200 gigapascal. Now let us take this session forward and let us try to discuss about one more modulus, that is the modulus of rigidity, which is also known as the shear modulus. Why shear modulus? Because the force acting is a shearing force or a tangential force, that's why. Okay. Now let me take a very basic case. I'll draw a plane diagram over here, like this. Okay, and when you apply shear stress, okay, like this, so this is tau. tau. What will happen? It is going to obviously deform. In what manner? In this manner. Let me just show you. Like this. Isn't it? This over here, this angle subtended is actually represented by phi. It's very small. Some force has been applied. There is a surface over here, isn't it? There is a surface over here, and parallel to that surface or onto that surface, a load has been applied, force has been applied, because of which this point A shifts to point A dash and point B shifts to point B dash. Then there is obviously some deformation. Let's say this is P and this is Q. Shear strain is defined as this, that is A dash divided by this, that is AP. So which eventually is tan phi. Okay. So this over here, this ratio is what is known as shear strain. First off, now all of this has to happen before the elastic limit. Before the elastic limit. Okay. And what I am considering is that both elastic limit and proportional limit are coinciding. Proportional limit are coinciding. Now before the elastic limit, again here also, if you try to do a test, let's say we want to make a plot. Plot of what? Plot of shear stress to shear strain. Shear strain is represented by phi. Shear stress is represented by tau. Okay. If you keep on applying a force over here, now this force has to be what? The force applied is not axial. The force applied is tangential. So when you apply a tangential force in mechanical engineering, that is referred to as shear force, right? When you do that, if you keep on increasing the value of the force, then there is going to be gradually increase in this over here and also this over here. So you will sort of get a plot like this, right? But a point will arrive after which if you keep on increasing the load further, the body will not be able to regain its original shape and size, and that's where plastic behavior comes into the picture. So once you reach this point over here is the proportional limit, and the stress corresponding to this proportional limit is represented by tau PL, after which if you keep on increasing the load further, you will reach here. Okay, this is the ultimate value, tau ultimate, and after which the material will rupture somewhere here. This is fracture and this is ultimate, and the stress corresponding will be tau F. So this is the kind of plot which you will get if you follow the same process that we had done in the tension test. Here the only thing which you need to remember that the force applied will not be axial and pulling outwards, the force will be tangential to the surface. That's it. If you do a test like that, you will get a plot. This is the shear stress, shear strain diagram. Okay, so we have to work within this region, and again this over here, this slope, shear stress to shear strain is nothing but a modulus which is known as shear modulus. It is also known as modulus of rigidity. So if I were to tell you the definition of modulus of rigidity, it would be like this. It is the ratio of shear stress to shear strain. Ratio of shear stress to shear strain is known or is represented by a constant which is known as modulus of rigidity, which is also known as shear modulus, because the force that we are considering is of a shearing nature. That's the entire idea behind modulus of rigidity. Okay, so there is a new strain. This is the strain, that is a shear strain, right? An axial strain comes into the picture whenever you sort of compress the material axially or you pull the material axially. There the kind of strain developed would be linear, but here this is sort of a different kind of strain. Okay, sort of an angular strain, right? Because there are simultaneously two change in dimensions taking place, one along this direction and one along this direction. So in order to take these two change in dimensions into account, that has to be represented by an angular deformation, and this is shear strain. Always remember this portion divided by this portion, or simply tan of this angle, that is the shear strain. Okay, now that we have understood shear strain, let us talk about bulk modulus. Let us see what that is. Now guys, bulk modulus is basically a term which you will get to hear about, especially in fluid mechanics. This is not something which is quite a regular occurrence as far as solid mechanics is concerned. This is very synonymous with fluid mechanics, because when you insert an object inside a fluid, there is pressure applied on that object from all the directions, say from X, from Y and from Z directions. So that material, okay, there is going to be an entire change in volume. Let's say if I am talking about this duster, if I insert this, okay, so if I insert this into a pool of water, what will happen? There is going to be a pressure acting on it from all the three directions, from the X, from the Y direction and also from the Z directions. Then obviously some change in volume is going to take place. Now let me just draw this properly. It would be something like this. So in the environment of solid mechanics, instead of using pressure, it would be something like this. Please watch this. There is going to be a force, let's say a compressive force in this direction, okay, from this direction also, and what else, from this direction. To be very precise, it's something like this, from here and also from the back. Sigma, let's say I'm writing it over here, sigma, then sigma and sigma. So along three mutually perpendicular directions, let's say sigma X, sigma Y and sigma Z. So if there is an object which is being subjected to a compressive stress along X, along Y and along Z, then obviously some dimensions, not some, in fact all the dimensions along X, Y and Z, they are going to change. If the dimensions change, if they are reduced, then the entire volume of the object would become less. So basically here we see a new type of strain that is known as volumetric strain. First of all, we see a new type of strain that is volumetric strain. Okay. So as far as bulk modulus K is concerned, bulk modulus K is basically a ratio of the normal stress sigma n with respect to the volumetric strain, that is the entire change in volume. So you can also say EV is equal to what? Change in volume divided by the original volume. This ratio is volumetric strain, and when you divide normal stress by volumetric strain, the constant that you get is a volumetric strain. Okay. So these were all the elastic constants that I had to talk about, and in the next session we will try to work out the volumetric strain in case of a uniaxial load, biaxial load and also triaxial load, right? So there are two more theoretical sessions in which we will be discussing a lot of derivations. The next two sessions will be very mathematical. So I'm pretty much sure that you must have got a very good idea as to what these elastic constants are all about, and let me just summarize. Elastic constants are factors which help you in determining the deformations, change in dimensions under different cases. First of all, when you talk about Young's modulus, that is going to help you in finding the change in length in the direction of load. Be it compression or tension, it is going to help you find the change in dimension. When you talk about what? Shear modulus or modulus of rigidity, this particular factor or this particular elastic constant is going to help you find the change in dimensions like this, as I have told you, okay, this and this. It is going to help you find these two dimensions with the help of this shear strain. And finally, as far as bulk modulus is concerned, this elastic constant is also very important, as it is going to help you find the change in volume with respect to the original volume. So if you know what the bulk modulus is, if you know the normal stress, you will easily get to know what the volumetric strain is. It's that simple. So these elastic constants really play a very important role. And let me tell you what we'll be doing in the next session is, we'll try to calculate the volumetric strains for all these three cases, and then in the final session, we'll sort of be calculating the stress strain relationship for a tapered bar, for a conically tapered bar, and also for an trapezoidally tapered bar. All of this and much more coming up in the next video. So guys, that was all for today. I'll see you again in the next video. Until then, take care. Have a nice day. Keep learning. Thanks.